Hello friends, in this video I am going to talk to you about the moment generating function. So what is this moment that this function will generate? The moments of a random variable x are nothing but the expectation values of its various powers such as e of x square, e of x cube. This value is sometimes also called the mean, and this value is sometimes also called the variance. So now, how do we find this moment generating function? The moment generating function is defined as the expectation value of e to the power tx, where t belongs to r. We will soon see why it's defined this way. So, e to the power x can be written as 1 plus x by 1 factorial plus x square by 2 factorial and etc. Similarly, we can write e to the power tx as 1 plus tx by 1 factorial plus t square x square by 2 factorial and the rest. Now, we will have to learn a property called linearity of the function e of x to go to the next step. So, what does linearity say? It is nothing but e of ax plus by, where x and y are random variables, is equal to a e of x plus b e of y. This simply suggests that the terms in summation or in subtraction can split into two and the constant terms can come out. Right. So now we are going to apply this property to our MGF. So the MGF was defined as expectation value of e to the power tx, right? So this e to the power tx came out to be 1 plus tx by 1 factorial plus t square x square by 2 factorial and the rest of this. Now we'll apply the linearity property that we just learned. This will make this equal to e of 1 plus e of tx by 1 factorial summation split e of t square x square by 2 factorial etc. Also, linearity ensures that the constant terms come out. That makes this into e of 1 plus t by 1 factorial into e of x plus t square by 2 factorial into e of x square plus the next term would be t cube by 3 factorial to e of x cube and the rest of the terms. So now you can see we are getting our moments here, here and here, right? So, what we got was, now the e of 1 we had gotten is defined to be 1. So, this term becomes like this. Now, we'll have to obtain these terms from this function. So, what can we do? We can differentiate this with respect to t. Say we differentiate with respect to t once. What do we get? So dt of dx, right? Differentiation of 1 gives 0. The next term gives 1 by 1 factorial, which is 1 into e of x plus 2t by 2 factorial into e of x square plus, if we had this term here, t cube by 3 factorial into e of x cube, we would get that as 3t square by 3 factorial into e of x cube, and so on. Now, to get this e of x, all we do is we put t equals 0. After putting t equals 0, so dt of this thing at t equals 0 gives e of x, and the rest of the terms, that is these terms, become 0 as all of them have t, and we are putting t equal to 0. So that's how we get the first moment. Similarly, to get the second moment, let's differentiate that function once more. So this was our function, right? So if we differentiate it once more, this is a constant, this goes to 0. This is a constant, this also goes to 0. Like, there is no t here, it's not a function of t, so it goes to 0. And this term becomes e of x square, right? And so this will become 3 into 2 by 3 factorial into t, some function of t, and all the rest of the terms will be functions of t. So this becomes t square dt square of e of tx becomes e of x square plus 3 into 2 by 3 factorial t e of x cube and other functions of t. So again we put t equals 0 and we obtain e of x square on a right hand side. So we spot a pattern here. The pattern is that to get the nth moment, we differentiate the moment generating function, n times and we put t equal to 0. This will be the MGF, which is written this way, and put t equals 0. Cool. So now we've done this. Is that the right emoji? I don't know. So now that we know how it gives the moments, let's find the moment generating function itself. So that is expectation value of e to the power tx. Now we need another property of expectation value called the lotus. This is a funny short form, but the full form is even funnier. It's called law of the unconscious statistician. So how does it go? It goes this way. So if I have expectation value of f of x, I get it as minus infinity to infinity f of x, the probability distribution of that random variable, this would be capital X, the random variable, into dx, just as we write this to be xpx dx. So we can substitute any function we have here directly here, just as we would do for the random variable. So this is a mistake that students tend to make, so it's named this way. Cool. Now we'll apply this to our moment generating function. So this would be minus infinity to infinity. This is all for the continuous case. For the discrete case, the integral will just become summation. This will be e to the power tx p of x dx. This is the probability distribution of the random variable. And yay, we are done. Hope this video increased the probability of you getting even higher marks in your next probability exam. Thanks for watching.